Let's begin. So, the Millikan oil drop experiment. Again, I'm going to fill in the gaps here for you today. So, an experiment performed by Robert Millikan in 1909 determined the size of the charge on an electron. That was basically what his actual purpose was, right? He was trying to find out how much charge there was on a single teeny tiny electron. He also determined that there was a smallest unit charge, or that charge was quantized. And he received the Nobel Prize for his work. We're going to explain the experiment here and show how Millikan was able to determine the size of a charge on a single electron. So this tells you how it's done. Jaden, are you paying attention here? Okay. Worried about are they getting any worse?
I don't know.
What Millikan did was put a charge on a tiny drop of oil and measure how strong an applied electric field had to be in order to stop the oil drop from falling. Since he was able to work out the mass of the oil drop, and he could calculate the force of gravity on one drop, he could then determine the electric charge that the drop must have. By varying the charge on different drops, he noticed that the charge was always a multiple of minus 1.6 times 10 to the minus 19. I'd like you to highlight that, because I don't know that everyone sees that in the research they do. And I think it's important. Okay? He found out that the charge on all these different ones was a multiple of that minus 1.6 times 10 to the minus 19. Now, what do I mean by a multiple? Travis, what does that mean, a multiple? Josh? Okay, well, say I came up with the number 4. What are the multiples of 4?
2, 1, 4.
2 and 1 would be factors.
4, 12,
Yeah.
12,
8, 12, 16, 36, 44, 96, 104, right? Those are all multiples. Yes, or multiply that number by some integer, right? Okay, so my imagination tells me, my guess is Millikan came up with these numbers, right? So let's just say that Millikan was coming up with, did you find it? There you go. Let's just say that Millikan came up with all these charges, right? So he would probably graph them. And he would get something along these lines like this, and then he would have found the slope. And if I was graphing these numbers, what would the value of the slope be? Well, it would be 4, right? Because you'd be graphing 4 and 8 and 12 and 16, right? And if you did the slope, well, it would be 4, right? But his number wasn't 4. His number was minus 1.6 times 10 to the minus 19. So he would get things like 1.6 times 10 to the minus 19, and 3.2 times 10 to the minus 19, and 4.8 times 10 to the minus 19, and 6.4 times 10 to the minus 19, and so on. Right? And now imagine he didn't have a computer, because this was 1909, right? He didn't have a computer to use Excel and find trend lines. He would have been doing this by hand. And would his numbers have been perfectly 1.6 times 10 to the minus 19, and perfectly 3.2, and perfectly 4.8? No! Right? He would have came up with all sorts of numbers, and he would have had to figure out this line of best fit by hand, wouldn't he? No computer. And many of you know that there was a little bit of controversy. One of the things that he did was, yes, there were some dots, some data points that were way all outliers, they call them. Great book, by the way, if you ever see it. Outliers. Has nothing to do with Millikan. It's a really good book. But an outlier is sort of an anomaly, something that doesn't fit the norm. Like if the Leafs ever win the Stanley Cup, that'll be an outlier. Okay? So now the controversy is that okay for Millikan to remove those data points? Some people say no, some people say it's fine. Like, I mean, if that data point way out there, that outlier was, if he thinks it was caused by some problem, well then okay, right? But a lot of people think that Millikan he had a number in mind, approximately 1.6 times 10 to the minus 19, and then he went looking for data that would support it. Is that the way scientists should work? No, probably not. And I have a video that sort of kind of plays into that a little bit later. Okay? So that's kind of this idea about this multiple that I want you to understand. He didn't just get an answer at the back and it wasn't some just perfect number, right? He did a lot of work. Okay. So here are the steps. An atomizer sprayed a fine mist of oil droplets into the chamber. So that's what this is right here. Here's an atomizer. It's just like a little spray bottle. And it sprayed the oil into this upper chamber. Some of these tiny droplets fell through a hole in the upper floor, which is right there. Millikan first let them fall until they reached terminal velocity, and using a microscope, he measured the terminal velocity and by use of a formula, calculated the mass of each oil droplet. Next, Millikan applied a charge to falling drops by illuminating the bottom chamber with X-rays. So he zapped them with X-rays, and this ionizes the air. What is an ion? Something to watch out for, you know? Keep your eye on it. But yeah, here, how about your own next week? What's an ion? It's an atom that, like, say for example, like lithium, +1, right? +1 means that it gives away an electron, it becomes +1, and it is now called an ion because it has a charge. No, it has a charge, not a neutral charge, it has a positive charge. Okay, so when the air is ionized, that means that the air particles, the oxygen, the nitrogen in the air, have become ionized, have a charge, and some of these electrons attach themselves to oil droplets. So the X-rays were to give the oil a charge. By attaching a battery to the plates above and below this bottom chamber, he was able to apply an electric voltage. The electric field produced in the bottom chamber. So we got a positive charge up top here, we got negative charge in the bottom, so we get this electric field, which I haven't told you a whole lot about. We get this electric field happening inside this bottom chamber. The electric field produced in the bottom chamber by this voltage would act on the charged oil droplets, and if the voltage was just right, the electromagnetic force would just balance the force of gravity in a drop, and the drop would hang suspended in midair. And here's a picture that you're going to draw many, many times in the next little while. Well, this little background. The weight force, out of the paddles are back there, the force of gravity down, but because of this electric field, you would have this electric force up. And those two, if he played with the voltage just right, he could get that drop to do what? Just hang there. It's suspended. Like it skipped days of school. It was suspended. A real funny thing. Right? They're balanced. Net force of 0. And then because he knew the mass, he could figure out the weight force and so on. Okay? So it says, now you try it here. Now I found, did you guys have a tough time finding a simulation that worked?
No.
Not too bad? Sometimes the Java updates were a problem and stuff like that. Here's what I found. I saw a few people found this one as well. If I was really organized, I'd go through this with you and sort of do it, but it's kind of complicated, so I think I'm just going to show you. So here's what Millikan's apparatus kind of looked like from the outside, right? Here's the microscope here, and when you start it, it sort of zooms like this, right? Okay, so now here's all these oil droplets, and you're going to see them in the microscope. They're going to appear. There's one right there. Now it's falling pretty fast, right? And you're probably supposed to use this timer down here to figure out how far it's falling and the time and figure out its terminal velocity. And then when you turn the voltage on and crank it up, oh, now how come this one's going up and how come that one's going down? It's bigger, it's got more mass, right? Okay, so here's one right here that I'm going to try to balance. Can you see that one? I'm going to try a different one. Okay. Okay, so Millikan would have to figure out the mass, and then with that voltage, now I've got the forces balanced on that one drop. Okay? And once you know the mass of that drop, then you can figure out the charge of that drop. And we could go ahead and do that. There's a voltage applied there, there's oil density, there's all these different calculations that we could do to really complicate. Okay? But I got two of them. We could figure out the charge on that drop. And it would be, again, some multiple of 1.6 times 10 to the minus 19. Negative 1.6. Right. Exactly. Okay, is this kind of filling in the blanks a little bit for you? Making some sense? Okay. Okay. So focus on the single falling drop. Adjust the electric field upwards until the drop remains suspended in midair. At that instant for the drop, the electric force on it exactly equals the force of gravity on it. Some drops have more electrons than others, so will require a higher voltage to stop. Once you're finished playing with the apparatus, close the window. Okay, so now let's look at the calculation that Millikan was able to do. When a drop is suspended, its weight mg is exactly equal to the electric force applied, QE. So mg is down. This FE, which I haven't told you yet, is Q times E. And because we know the FE, how do I know the FE? It's the same as the weight force, because I know the FE, and I know the electric field strength based on the voltage. I can figure out what this value of Q is. That's what he was trying to figure out. What are these charges? The values of E, the applied electric field, and M, the mass of the drop, and G, the acceleration due to gravity, are all known values, so you can solve for Q, the charge on the drop. Millikan determined the charge on a drop, and then he redid the experiment numerous times, like day after day after day. Boring. Each time varying the strength of the X-rays ionizing the air so that the differing number of electrons would jump onto the oil molecules each time. He obtained various values for Q. And this charge Q on a drop was always, again, a multiple of minus 1.6 times 10 to the minus 19, which is the charge on a single electron. It's also the charge on a single proton. It's positive 1.6 times 10 to the minus 19. This number was the one Millikan was looking for, and it showed that the value was quantized. In other words, it is the smallest unit of charge, was this amount. And it was the charge on a single electron. You can't get a smaller amount of charge. Zach, when I walk into co-op, sometimes I buy eggs. What are my options buying eggs? I can buy size-wise. I can 18s, 6s, 12s. Do you guys get them in like the flat 24? And then you put them in the... Yeah. Okay, so you can buy 6 of eggs, you can buy a dozen eggs, you can buy 18, I think you can buy 24, you can buy, I guess you can buy a pallet of eggs too if you want, right, from your store, right? But the smallest amount of eggs you can buy, or that you can get, is a single egg, right? I can't walk in and say, I want half an egg, cut it in half for me. Doesn't work, right? You can't. You get my point, right? That's the smallest amount there is. Right? So that's what quantized means. You can't get any smaller. That is the smallest amount of charge. Okay. Okay, so I'm going to give you some introductory information now about electric fields. Very similar to gravitational fields. We're going to sort of compare them and come up with some differences and that kind of thing. Okay, so follow along with me, please. You should have a highlighter or a pen or a pencil, something like that, to sort of make some notes in the side. Here we go. The space around a strong magnet is different from how it would be if the magnet were not there. Put a paperclip in the space and you'll see the paperclip move. The space around a black hole is different from how it would be if the black hole were not there. Put yourself in that space, it'll be the last thing you do. Similarly, the space around a concentration of electric charge is different from how it would be if the charge were not there. If you walk by the charged dome of an electrostatic machine, a Van de Graaff generator, for example, right in there, right? I have to check the belt to see if it works. I'll come in on the weekend and see if it works. You can sense the charge. Hair on your body stands out, some of you more than others, depending on your hairstyle. Just a tiny bit if you're more than a meter away, and more if you're closer. In fact, the closer you get to it, the stronger the electric field. Right? Much like gravity. The space that surrounds each of these, the magnet, the black hole, and the electric charge is altered. The space is said to contain a force field. Right? A force field. Okay, so electric fields. The force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it curves because there is an interaction between the ball and the earth, between their centers of gravity to be exact. Their centers of gravity are quite far apart, so this is action at a distance. We talked about this in gravity, right? I can't pull on the scissors using Jedi mind tricks. The only way for me to pull the scissors is I actually have to touch them, right? But gravity, if I drop the scissors, it can pull them, right? The Earth has this gravitational field. I have a gravitational field, it's just that it's not strong enough to attract the city. I'm not that attractive. I need to be way bigger. Way bigger. The idea that things not in contact could exert force on one another bothers Isaac Newton and many others. The concept of a force field eliminates the distance factor. This is key. The ball is in contact with the field all the time. We say that the ball curves because it interacts with the Earth's gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the mass of the Earth and other astronomical bodies that are responsible for the field. So here's the Earth. Here's the gravitational field with the arrows pointing towards the center, right? And if you put an object in there, well, it's in contact with the field, right? There's that contact that we need. So we've sort of imagined this force field model, I guess, if you will. If you want to go back to that first month where we talked about models, we've imagined this force field model to better explain what we're talking about. And of course, an explanation is the theory, right? Remember that theory don't become law stuff, right? Okay. Just as the space around the Earth and every other mass is filled with a gravitational field, the space around every electric charge is filled with an electric field. Oops. Right? Every electric charge. Anything that has an electric charge has an electric field. When you pull your socks out of the dryer, they have a charge. It has an electric field. A small electric field, right? When you rub the balloon on your head, well, you do, I don't. It's charged and it has an electric field. And if you put little bits of paper, it might be attractive, right? Yeah, that's cool. Yeah. Go ahead, kid. In figure 33.2, a gravitational force holds a satellite in orbit about a planet, and an electrical force holds an electron in orbit about a proton. In both cases, there is no contact between the objects. No contact between the objects. And the forces are acting at a distance, or acting without contact. That's probably a better way of putting it, right? Instead of acting at a distance, it's acting without contact. I can act on the scissors at a distance if they're tied to a string, right? But I can't act without contact. Putting this in terms of the field concept, we can say that the orbiting satellite and electron interact with the force fields of the planet and the proton and are everywhere in contact with these fields. In other words, the force that one electric charge exerts on another can be described as the interaction between one charge and the electric field set up by the other. So here's the proton, and it has its electric field, and that electron is in contact with the field. Is that making sense? Because I didn't really sort of explain that really, really well in the gravitational field scene. Now, an electric field has both magnitude and direction. Vector. Oh, yeah, I hear what you're saying, yeah. Right. It is a vector quantity, right? Its magnitude or strength can be measured by its effect on charges located in the field. Imagine a small positive test charge that is placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Well, of course. Where the force on the test charge is weak, the field is small. Let's look at the little footnote there. The strength of an electric field is a measure of how great a force will be exerted on a small test charge placed in the field. In other words, the bigger the field, the bigger the force. And the bigger the force, the bigger the field. The test charge must be small enough that it does not push the original charge around and thus alter the field we're trying to measure. If a test charge Q experiences a force F at some point in space, then the electric field E at that point is, and this is the first time you've seen it, the electric field, oh, I'm doing it in a highlighter, F over Q. Yeah, whoa. That does kind of hurt to look at it up there, doesn't it? Yeah? I'm going to adjust that for you. E equals F over Q, right? E equals F over Q. Okay, guys, I need you to focus, okay? Don't talk about Talon's food. Just listen. I know it's really hard to listen to me for 20 minutes, okay? Please try. Everything that I say is a step in the process. If you miss 3 or 4 steps, you're not going to understand steps 4, 5, and 6. I know it's hard. Stay with me. Right here. The direction of the electric field at any point by convention is the direction of the electrical force on a small positive test charge. I did it again. Okay? That, my friends, is important. The direction is on the direction of the electric field at any point by convention is the direction of the electrical force on a small positive test charge placed at that point. So by convention, all the scientists in the world said, hey, let's use the positive test charge. And everyone else had a great idea, let's do that. Could they get a big meeting of all the scientists in the world and say, let's change it to negative? No. Sure they could. Would everyone agree? No. People don't like to change and people don't like to agree on things. How this ever happened in the first place is beyond me. But one person said, let's do this, and then he was the first one. Shoot. Who knows? Okay? But it's a convention. It's like saying red means stop. Okay? So we use a small positive test charge. And this is because gravitational fields always do what? They always pull. Electrical fields can pull, but they can also push. So there is a change in direction. That's why we need that. Okay? So thus, if the charge that sets up the field is positive, the field points away from that charge. You should draw this on the side. So if you've got a positive charge, your little teeny tiny positive test charge is going to go away, isn't it? Right? So the positive charge object has a field that goes away, and a negative charge one would look like what? That positive test charge would come towards it, wouldn't it? Just like gravity. And if I used negative test charge, well, then these would be flipped, right? That's why we need that. Be sure to distinguish between the hypothetical small test charge and the charge that sets up the field. Okay. Electric field strength can be measured in units of newtons per coulomb. I believe that's in the project, is it not? Electric field strength can be measured in units of newtons per coulomb. Now, electric field lines. Here's another topic that I could have talked about in gravitational fields, but I waited till now. Since an electric field has both magnitude and direction, it is a vector quantity, can be represented by vectors. The negatively charged particle in figure 33-3 top, that's one over here, is surrounded by vectors that point toward the particle. Do you see all these arrows here? These are all vectors. If the particle were positively charged, the vectors would point away from the particle. The vectors always point in the direction of the force that would act on a positive test charge. We've been through that. Now, the magnitude of the field is indicated by the length of the vectors. Notice that the electric field is greater where the vectors are long than where the vectors are short. Right? So where are the vectors long? Close. And farther away, they get smaller and smaller. And like out here, they'd be just dots, right? But in tight here, they are long. Now, if I went even closer in, well, they'd be so long that they might actually go across, right? And if let's do them all in black. If I were to draw every vector from every point, it would be a solid circle that is nothing but black. You wouldn't be able to see any vectors at all because it would be completely covered. It'd be useless. Right? It'd be useless. The same is true for gravitational fields. Okay, so such a diagram would be totally unreadable. I almost said that in a Trump voice. A more useful way to describe an electric field is with electric field lines. Adam, are you paying attention with us? Also called lines of force. This one, these are not vectors. And the second one, these are electric lines of force, or electric field lines. And where the lines are farther apart, the field is weaker, just like gravity. Just like gravity. Okay? So where they're far apart like this, weak. Where it's in close here, strong. For an isolated charge, and when I say an isolated charge, I mean a single charge all by itself. The lines extend to infinity, while for two or more opposite charges, the lines emanate from positive and terminate on a negative. Some electric field configurations are shown in figure 33-4. So this is an isolated charge. These arrows go forever. They're like the rays you learned about in geometry years ago, right? Positive, negative charge, so the lines go from positive to negative, from positive to negative, right? Away from positive towards negative. When you've got charged plates, always from positive to negative. Someone this morning said to me, this looks like, what does it look like that you may have seen in earlier science classes? It does actually look like the cell splitting in biology. You're right. That's not anything what I'm talking about, but you're right. That does look like that. Seen a magnetic field before? Yeah, with a magnet, right? Okay, so here I'm going to show you some pictures. On the next page here are some actual pictures. I need about 4 more minutes here. No, maybe 5 or 6. Stay with me. Stay with me. Okay. Adam? 4 more minutes of concentration. Awesome. I'm just looking at you. You're just vibrating now. You can see. Photographs of field patterns are shown in figure 33-5. The photographs show bits of thread that are suspended in an oil bath surrounding charged conductors. The ends of the bits of thread are charged by induction and tend to line up end to end with the field lines, like iron filings in a magnetic field. Notice that between the plates, the threads are aligned parallel to each other. The field has a constant strength between the plates. Also notice the threads inside the cylinder are unaligned. There is no electric field in the space inside a conductor. The conductor shields the space from the field outside. So let's look at these pictures here. Now, what can you tell me about, these are the two charged objects. What can you tell me about them? Do you know whether they're positive or negatives? One of each? How do you know, Adam? Yeah, you're exactly right. So one's positive, one's negative. We don't know what direction, but they're sort of connecting, right? What do you say about these ones over here? Both this, yeah, either both positive or both negative, and they don't connect. They do this exactly. Awesome. These are two charged plates over here. You can't really, again, you can't really tell which one is which, but they're like this, right? And then at the end they kind of curve like that. This here is a charged plate, and you see that they go like this to this thing here, right? And you'll notice what they said was that inside this, is there a field? No. There is no field at all. This is what's known as a Faraday cage. You hear this from time to time in movies and TV shows. It doesn't affect you. It shields you. Have you ever been inside the rotary arena with your cell phone?
Yes.
Does it work?
No.
How come?
No.
Because it's a Faraday cage. What's the rotary arena made out of? It's made out of metal, isn't it? It's a big metal building. And even though, no, there's no battery hooked up or anything, it's a big metal building. It's a type of Faraday cage, and it's not allowing, there's no field inside, it's not allowing that penetration. Okay? You do hear it from time to time, like I said, movies and TV shows. You ever seen the old series Lost? They talk about Faraday cages, right? Can you explain the ending to me, Anna? You don't get the ending? You can't spoil that ending. You can't spoil it. Awesome. I don't know. Another movie, I've been watching Timeless, and it's a time travel thing, and I think they talk about Faraday cages in there as well. So if you hear that, you go, oh, hey, I know what that is. Okay. One last thing here, and then I'll be quiet. If our only concern for electrical forces were limited to isolated point charges, the electric field concept would be of limited use. Give me 3 or 4 more minutes, you guys. Hang on there. The force between point charges is adequately described by Coulomb's law, but charges most often are spread out over a wide variety of surfaces. Charges also move. This motion is communicated by neighboring charges by changes in the electric field that emanate at the speed of light. When you have charges in motion, we call that? Nobody knows? Runs along the wires?
Current surge.
Electricity. Charge is in motion. That's called electricity, right? As later chapters will show, the electric field is a storehouse of energy. The energy can be transported over long distances by electric field, which can be directed through and guided by wires, or directed through empty space. Okay, last little bit right here. This little square over here in the right-hand corner. Suppose that a beam of electrons is produced at one end of a glass tube and lights up a phosphor screen on the inner surface at the other end. So we've got a glass tube. It's kind of firing out electrons, right? And there's a sort of a screen at this end here, and on the inside screen there's this coating of phosphorus. And phosphorus, when it's struck by an electron, will glow. It'll just like a white light. Okay? Now, when the beam is straight, it produces a spot of light on the middle of the screen. So if you're the human over here looking at it, you're going to see a little white dot right there. Okay? Now, if the beam passes through the electric field of a pair of oppositely charged plates, it's deflected, say, to the left. Now, I've got kind of things reversed here a little bit, but let's say I've got my electric plates here, positives and negatives down here. So my electron beam is going to be deflected, and my spot of light's going to be there. Now, if I reverse the charge on those plates, if I make the top instead negative and the bottom positive, where's the electrons going to go? Kind of like that. Now, about 15, 18 years ago, I could say to you, does anyone care about this? And most people say, no, we don't care about that. But I would say you're wrong, because you all have one of these in your house. That's not true anymore. So can you think of something that kind of reminds you of this, that people would have had 15 years ago, that some of you might still have?
Box TV.
Box TV. Oh, the old tube TVs. Maybe grandma still has one. You still have one? Okay, so Teague, what happens, and this tends to happen with old ones, what happens when you unplug it? And it makes that noise. It does it. Right? And all the light goes down to the middle. So what's happening there is that, yeah, lots of static, electric field. Right? Oh, wow, right? Yeah. Yep. Okay, so what's happening is, when Tegan plugs that old TV, is that electric field inside is suddenly turned off, and the electron beam, instead of being deflected, goes all towards the center. Now, how does it work? How does this TV work? Well, that electric field is changed so that beam goes like this, back and forth across the screen, but really, 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 really fast, so fast that you can't see it, right? And your eyes just see that as a picture. And if you look really close at the screen, you'll see that it's actually made up of three colored dots, right? The three, red, blue, green, right? The three primary colors, so that's how you get your color TV. Okay, so that's how old school TVs work. I don't know how they will work. Anyways, so they do use that electric field. Yeah, you can wreck those old ones if you take a really strong magnet. Yeah. And because magnetic fields and electric fields are kind of, they're related.
I remember I used to stumble if I had a vacuum cleaner.
Yeah. Yeah. Okay, I'm going to be quiet. You got a few minutes left. If you need to do some filming or something with that project, you can spend some time on that. There are a few questions here. I would strongly suggest you guys do those over the weekend. Great, I'm still talking. Yeah, what did I say? Yeah, I'm still talking though. I'll tell you when I'm done. There are some questions there on the back page. You should probably do them. You should be aware of the answers. I'm going to quickly go through those answers on Monday. Okay, and then we'll move on with some problems.